So please, sir.
All right, thank you very much for the introduction. Hello, everyone. My name is Yiqiu Zhao. I'm now a postdoc working with Professor Qin Xu at Hong Kong University of Science and Technology. So this is my great pleasure to share some of our recent works to you. And this work was also done with collaborators from Los Alamos National Laboratory and Nanyang Technological University of Singapore. So we are interested in the physics of soft materials, soft composite materials, which are slightly different from glasses, I think. So which refers to the soft polymeric elastomers loaded with stiff functional inclusions. And such a system forms basis of wide-ranging applications from smart biomedical devices and soft actuators to synthetic tissues, flexible electronics, and biofilms. So in all these cases, the design of material function relies on our understanding of how does these included particles interact with each other and with the matrix to give rise to global desired properties. So to study this question, we start by considering the classic simplest model consisting of stiff particles embedded in an elastic medium. So in the dilute case, the problem is very well understood by considering only isolated inclusions and their coupling between the elastic environment. However, the case becomes much harder for dense composites because continuum mechanics calculations suggest strong stress concentrations and even singularities for nearby particles when they are close enough to each other. Furthermore, if the matrix is soft enough, we should also consider the non-affine shear transformations and the multi-phase nature of the matrix. For example, a soft polymeric gel usually consists of a fairly dilute cross-linked polymer network with a lot of free chains that are basically viscous fluid. So, which we speculate might leave room to the formation of contact networks of the included particles, like those seen in granular materials. So all these issues makes it extremely challenging to model soft composite materials in the dense and soft limit. And our work here, we hope to bring some insight by our experiments and a phenomenological model based on criticality. So our experimental system consists of those composites made by dispersing these micron-sized PS particles in a much softer PDMS elastomer. So we have these cylinder-shaped samples, and we measure their mechanics using a renometer. So what we do is we apply an axial compressive strain to the system and monitor the change of the torsional shear modulus. So we noticed that in our sample, if you compress it vertically, the material dilates in its radial and azimuthal directions while maintaining a constant volume. So that what we are measuring is actually an evolution of shear modulus under a pure shear deformation of the sample without changing the volume fraction. So our specific model for this experiment is to understand how does the interplay between applied strain and the volume fraction particles and also the shear modulus of the matrix together determines the overall composite shear modulus. So these are some typical measurements from our experiments describing the relative modulus of the system changes to its axial strain. So we see that before this 0.2 axial strain, there is a stiffening regime for all the samples. And above 0.2 strain, we saw permanent deformation of the system, and we are not super interested in that regime. So for the stiffening regime, we saw that the material with softer matrix and denser composites have stronger stiffening, which as one might expect it, I think. So to get some quantitative insights, we look at the two limits of the stiffening regime. We plot the maximum stiffened states and this undeformed states and show their relative modulus as function of volume fraction. So we show that in both cases, the results deviate significantly from the classical series, ignoring interactions among the inclusions. In particular, these maximally stiffened states demonstrate a strong evidence for divergent trend near some particular volume fraction about 0.6, which is usually what observed for spherical particles. So we speculate that there is some relation to the granular jamming over here. So to check this, we put the same particles we used to fabricate these composites into a viscous fluid and measure their steady flow rheology. So we found that the steady state viscosity can be captured very well using this power law with a fitted diverging volume fraction about 0.6. To show that this is indeed a rigidity transition there, we also prepared suspensions with volume fraction beyond and measured finite modulus over there, so that we conclude that this 0.6 is indeed captures a rigidity transition of the particle phase without the elastic matrix. However, the question here is, there are certainly some relations, but how can we incorporate this rigidity transition of the particles into modeling composites? So what we did is motivated by analog to the Yiqiu model, where we see some similar behaviors if we compare the shear modulus of system to the magnetization as an order parameter. And if we do that, the role of the matrix modulus in our system appears to play a similar role as a magnetic field in the Yiqiu model. So with that in mind, we can identify various critical scaling laws and identify critical exponents in analogy to a Yiqiu model. So why are we interested at this? Because from those critical scaling laws, we may bring up scaling answers, which, if true, would release the relevant material parameters, for example, the volume fraction of particles and the shear modulus of matrix to the overall shear modulus of the composite, which will answer the question that we bring up originally. So we show that under proper rescaling, indeed, all our measurements collapsed very well into these two distinct regimes according to their volume fraction to be either above that granular jamming fraction or below this granular jamming fraction. We show that the parameters are spanning 2 orders of magnitude, so we think it's a fairly good collapse. So with that in mind, it suggests that the physical picture we proposed is kind of makes sense. And this is a phase diagram in analogy to the Yiqiu phase diagram in the space of temperature and magnetic field. So although there's no phase transition over here, but we argue that the appearance of these critical points actually separates the behavior of the composites into 3 asymptotic regimes that can be seen by looking at the scaling collapse. For example, the slope 1 here suggests in this regime, the composite modulus will scale linearly with the matrix modulus. So we call it matrix dominant. And over here, the composite modulus kind of independent with matrix modulus. So we call it particle dominant. And there is, of course, this critical regime where the contribution from particle and matrix are strongly coupled. So aside from this physical insight, we can actually also construct some phenomenological model by assuming that the system should sit at a minimum of some phenomenological free energy. With this free energy has some scale invariant form describing the jamming transition. So I don't want to go to details of that. So far so good, but we appears only be able to model this maximally stiffened state, which is only a limit of the strain stiffening regime. So what happens in other states, which apparently depends on strain, and our model so far doesn't depend on strain. So what we do is that we found it's operationally really simple. We just need to replace the original jamming volume fraction to be a strain dependent value and kept everything else the same. With that, we can collapse all the data within all the strain stiffening regime to a single plot. Okay. So then the remaining question is, what's the physical meaning of this parameter? So if we plot the 5G values, the jamming volume fractions that we use to collapse the composite data, we show that its shape really resembles the granular shear jamming boundary. And indeed, the meaning of this line in our model should capture a rigidity transition line in the limit case of 0 matrix elasticity. So to test whether if this is really the case, So we, if you remember, we already showed that there is a rigidity transition over here if you cross the phase boundary over here. And we also show that in simulations, if you cross the phase boundary over here, you have a frictionless jamming point. We also conducted additional, okay, thank you. We also conducted additional suspension experiments that showing that if you apply quasi-static uniaxial compression, there's a lot of details here. But basically, we can confirm that there is a rigidity-induced rigidity transition in the limit of zero matrix elasticity. So to summarize a little bit, if we know that the form of that jamming phase boundary, we can arrive at a quantitative model using these three equations that relates the three interested parameters to the overall response of the composite materials. So in short, we also tried a different material, replacing the PS particles with glass beads and everything basically the same. So okay, this I think is fun assignment. So I think our experimental evidences suggest such a physical picture that if we consider the phase diagram spanned in this three-dimensional space, where this is volume fraction, this is matrix elasticity, and this is applied deformation, all our composite elastomers live in the space with finite matrix elasticity, and there's no phase transition in this space. But the suspensions, which defined by dispersing particles in a viscous fluid, lives in the space of zero matrix elasticity, and there is indeed a rigidity transition boundary over there. So although there is no phase transition for composites, the appearance of this phase boundary would affect the behavior of the composites, such that if we strain a given composite sample, it is likely to cross over from a matrix-dominated regime to a particle-dominated regime. If the matrix and the particle has stiffness widely separated, then it would induce a giant strain stiffening of this material. So with that, I want to leave this slide and take questions. I just want to have a final word that we have a draft on archive. So if you are interested, I would really love to talk with you. Thank you.
Thank you very much. So question.